All right, welcome back to another episode of Science with Surback. Today we're talking about section 5.3, which deals with electron configuration. Before we get into the details of these notes, here are a few objectives I would like you to be able to meet by the end of this video. Objective number 1, apply the Pauli exclusion principle, the Avpu principle, and Hund's rule to write electron configurations using orbital diagrams and electron configuration notation. And objective number 2, define valence electrons and draw electron dot structures representing an atom's valence electrons. So let's get underway here with section 3. And this is a really nice section because it ties together information in sections 1 and 2, and it concludes this chapter. So electron configurations are defined as the arrangement of electrons in atom or in a atom. Now, what happens here is this. We've talked up to this point about the electron, how it was discovered, and the work that was discovered. That was section 1. Then in section 2, we specifically designated these locations where an electron can be. Remember, the major thing with section 2 was that it no longer confined the electron to a circular orbit. It gave those regions which we call the orbital, and those orbitals are where the electron can most likely be found. Now in this section with electron configuration, we can specify what electron we're talking about and associate that with an orbital. So essentially what we're doing is we're given an address for each and every electron, and we can add the other details that we've talked about already in this section. Now, one thing that we'll talk about here is ground state versus excited electron configuration. So ground state says, hey, the electron's going to occupy the lowest energy level possible. That's its whole goal. Now, when energy is added to it, the electron will bump to different letters or different levels and have additional energy added to it. So let's take a look at a couple of things to go over. And we're really just jumping into what electron configuration can be. So what I have here is this. I have a periodic table, and what I did with this periodic table is I took, and where normally we have 2 rows at the bottom to make the periodic table look nice, I went ahead and I squished those rows, or I inserted them into where they should be in the periodic table. So again, all this is the periodic table with these 2 rows, the lanthanide and the actinide series, we call them, smushed back into the periodic table. So I call this the extended periodic table. And one thing I want to change about this is that we shouldn't have this business over here. So I'm going to X that out. And for our business, or for our periodic table here, the helium should be on the left-hand side. And again, this is just for the periodic table, for the extended periodic table that we have. So we need to tie our electron configuration to this box right here. So what I'm going to do is this. I have that same periodic table that I just showed you, but it's color coordinated. Now, what I have here is this. I have, or what I'm going to fill out, is the electron configuration periodic table. And so what I'm going to do here is I am going to divide the periodic table into distinct sublevels. And we talked about the sublevels in section 2. So this blue sublevel here is known as the S sublevel. And again, the S sublevel consists of 2 columns of the periodic table. Now I shift over here to the column of 6 red groups, and this section right here is known as the p sublevel. And then I'm going to go back towards this orange section. And this section of the periodic table is known as the d sublevel. And our last section here, this beige section or tan section, is known as the F sublevel. Now, these letters should sound familiar because in section 2, remember we talked about the s, p, d, and f orbitals. Now what we're going to do is we're going to specify that electron configuration, which I said on the opening slide was essentially an address that we have here. So what I want you to do is I want you to fill in this periodic table, and I'm going to fill in the first box, which is associated with helium, and it's going to be 1s1. Now, you may be sitting there wondering, okay, well, what does 1s1, or what is that series of letters and numbers represent? Well, let's break this down here. So I'm going to blow this up, and the first thing that I get to is this large number 1. And this number represents the energy level of the electron. And I'm going to abbreviate electron here as E to the minus. Now, this S represents the sublevel that the electron exists in. And then the little superscript number that we have here, this right here is the electron number, or the number of electrons within that specified sublevel and energy level. Now, when we get to that second box, which represents helium, what we would do, we are still in the first row, which tells us we're in that first energy level. So we start out here with a 1, and we're still in the S sublevel, so we start, again, that letter with an S. However, we're in the second box, so this second box represents that we are talking about the second electron in that 1s sublevel. Okay, so now we got the first row down. We'll move to the second row. And so our second row, again, for the S sublevel, the second row represents the energy level. So we're going to start out with a 2. It's still in the S sublevel. That's what this top portion designates here. And then we restart our numbering because this is the first electron in that 2s level. Okay, so it's 2s1. Over here, which would be beryllium, it's still in the second energy level, also in the S subblock, and it is the second electron of the 2s level. All right, so now we shift over here to the P level. It is still in the second row, which means it's in the second energy level. So we say, hey, it's in the second energy level. And then we have a P because it's in the P sublevel, and we have 2p1. The second box here, which is carbon, that's the carbon box there, is still in the second energy level. It's still in the P sublevel, so we have 2p2. Then the next box over is 2p3. The following box is 2p4, 2p5, and 2p6. Okay, so now we're going to get a little bit of a pattern here. The third energy level, represented by the third period, is going to start off here with 3s because we are in the third energy level, the S sublevel, and that is the first electron in the 3s level. we shift over a box, and we go and we call this the 3s2 box, which represents the second electron in the 3s level. And then we go over here to the p block. So the p block, we're still in the third row or third energy level. We've shifted to the p block. Our numbering starts over because now we're in the 3p sublevel. This next box would be 3p2, and we're going to go all the way over to 3p6. We then get down to the fourth energy level. The fourth energy level, again, is represented by the fourth row. It's still in that S subblock, and it has the first, or the superscript of 1, to be at that 4s level. We shift over to the next box. It's 4s2, and then we need to pause for the D sublevel. The D sublevel, the energy level, is no longer equal to the row. The energy level here is equal to row minus 1. Okay, so I'm going to put this: the energy level of our d electrons is equal to row minus 1. So the energy level, because we're in the fourth row for these d electrons, is 4 minus 1. So our first orange box here, which would represent scandium, is 3d1. The next box over is 3d2. And we're going to do this all the way to 3d10. Okay, now we get back to the red boxes. Remember, the row is equal to the energy level for the p sublevel. So this first box is 4p1. The second box is 4p2. Third box is 4p3. And we'll do this all the way over until we get to 4p6. We shift over to the fifth energy level, which the S sublevel, the row is equal to the energy level. So we start again with the 5s1, 5s2. We get to the D block. Remember, the energy level is row minus 1. We're in the fifth row. So 5 minus 1 is 4. This first orange block, which represents yttrium, is 4d1. Okay. The next box over is 4d2, and we're going to do this until 4d10. Okay, so now, again, we have 4d1 all the way to 4d10. We get to the p sublevel, and remember, the p sublevel, the energy level is equal to the row, so we go back to 5p1, and we write all the way down to 5p6. We go to the sixth energy level. S sublevel, the energy level is the row, so we have 6s1, 6s2, and then we got to pump the brakes. The F sublevel, the energy level, we now have to do not row minus 1, but row minus 2 to find out here what is the energy level. So again, row minus 2. So we start out here with this. We're in the sixth row. 6 minus 2 is 4. And so this 4s 4F1 box would represent lanthanide. So 4F1 would represent lanthanide. This next box would be 4F2, and we would do this all the way over to 4F14. Now we get to the D sublevel. The D sublevel, remember the energy level is rho minus 1. We're in row 6, so this box here, which represents our next element here is 5D1, and we do this all the way to 5D10. Now, we go to the P sublevel. Remember, the rho is equal to the energy level. So we go back to 6P1 all the way over to 6P6. All right, last row of the periodic table here that we have. 7th row for the S sublect, the start here with francium as 7s1. 7s2 is the next box. Remember, the energy level for F is rho minus 2. We're in the 7th row. 7 minus 2 is 5, so this first box becomes 5F1. We go all the way over until 5F14. Now, the energy level for the D sublevel is rho minus 1. We're in the 7th row, so this would become 6D1 all the way over to 6D10. We get to the P sublevel. The P sublevel here, remember the energy level is equal to the rho, so this first box would be 7P1, and we can scroll over to our final box, which is 7P6. Okay, so what this represents is our electron configuration periodic table. And we can now specify the electrons that are in this particular box. All right, so we move through here. We will utilize this, so keep this handy. But we move through, and we want to know how do we use that periodic table to write the electron configuration. So the first thing that we're going to do is we are going to locate that element that we're looking for on the periodic table. We're going to find that and correlate that information or correspond it to that information on that table we just went over filling out. And then we are going to write down the subshells in order. But we only need the last bit of information. So if that box takes up the entire subshell, We'll only write the final right subshell. And that will make sense as we go along. Now, I'm going to show you the longhand version and then the shorthand version. We will go back to the previous noble gas, we'll put it in brackets, and we'll write it from there. So let's go ahead, let's try to apply these steps, and we'll bounce back and forth from the periodic table. So we go through this, write the complete electron configuration for these elements. The first element that we have is phosphorus. So we look on the periodic table, we find P for phosphorus. It is element number 15. Now, what I do is I take that periodic table we just looked at and we correlate that box, which we have to be careful here, but phosphorus would be here at 3p3. So what that represents is our stopping point, okay? So now, that is our stopping point here, 3p3. What we have to do up to this point is now write every bit of the electron configuration up to that point. So we start just like we would read a book. We start in that S subblock, and we start with the 1s. We ask ourselves, have we reached 3p3 or phosphorus? Well, the answer is no. So what we do is we do this. We write down just 1s2, and that represents that we have all of those electrons in that 1s level. There's nothing else in the first energy level, so we move down to the second energy level. We have 2s. We ask ourselves, is it 3p3 or have we reached it yet? Nope. That means we need all of those. So to represent that we have all of those 2s electrons, we write down 2s2. Scroll over to the p subblock. We ask ourselves, is that containing 3p3 or phosphorus? Nope. So we represent, or we write down 2p6 to say we need all of those electrons. Get to the 3s level. We ask ourselves, have we reached 3p3? No, we still haven't, so we need to write that down as 3s2. Then we get to the p subblock, and we ask our 3p level, have we reached our phosphorus? Well, yeah, it's right here at that 3p3 level. So we don't need to write all the way to 3p6. We only want to represent the electrons we have. And so we would stop right there at phosphorus at 3p3. So right there for phosphorus, that would be the complete electron configuration. Now let's go and let's try to write the electron configuration for indium. So indium is represented by the symbol In. Element number 49. We correlate that number, element number 49, to that periodic table. And I'm going to shift over here to the right. Indium, element number 49, is right here at 5p1. So 5p1 is going to be our stopping point. Now what we do is we write out the electron configuration just like we did last time. Our stopping point is 5p1. So again, we start in the upper left-hand corner. We ask ourselves, 1s, is that containing 5p1? Answer is no. We need all of those electrons, so 1s2. Go to the second energy level. 2s, is that 5p1? No. We need all of those electrons, so 2s2. Is it in the 2p level? No. We need all of those electrons, so we write down 2p6. Is it in the 3s level? No. So we write down 3s2. Is it in the 3p level? No. So we write down 3p6. Is it in the 4s level? No. We need all of those electrons, so 4s2. Is it in the 3d set of electrons? No, and be careful here. It goes 4s2, 3d10, since we need all those. Is it in the 4p level? Still no. 4p6 to represent that we need all of those. We go down to the fifth energy level, 5s. Is it there? No, it's not in the 5s level, so we need all of those electrons. Still not in the 4d set of electrons, so we write down 4d10. And then we finally get to our stopping point. We're in the 5p section now. Where we needed to stop was 5p1. So our final bit of information here is 5p1. All right. That's a lot of work. So we do have a shorthand method here. So I'm going to get the next slide here, and I'm going to show you that shorthand method. So with the shorthand method, what we need to think about here is our two elements. So we start out here with radium, Ra. Radium on the periodic table is right here, element number 88. That, if you look at the periodic table, would be a lot of electron configuration to write. So element number 88, if we correlate that on the periodic table, it is 7s2. Now, I'm going to keep my periodic table handy, and I'm going to highlight a few things. And that thing that I'm going to highlight is this group or column on the right-hand side. This group or column on the right-hand side is known as the noble gases. So this row right here is known as the noble gases. Now, one thing, because we crossed this out, included in that, I'm going to put just a little arrow here, includes He or helium. Okay, so these rows, this is what we're going to use. So to write the electron configuration, we found radium. We don't want to write all that business down, so we go up a row all the way to the right. We find that first noble gas, and that is radon. So we write down in brackets Rn to represent that we have radon. And that says that we have accounted for every electron up through radon's electron configuration. Now what we do, we start by identifying radon, and it's like we've just written 6p6. We've gone through that. So we move to the next level, which is a 7s level, and we ask ourselves, hey, is the radium in 7s? Well, it is. It's the second box there. So all we need to do to write this down is put 7s2. Now, we move to bismuth. We do the same thing. So bismuth, Bi here. Bismuth is element number 83. To start out this, we look one row above and to the right, and we find element xenon. It is the first noble gas, and so we write Xe in brackets, and that represents that we have all the electrons through xenon. So again, xenon here is represented by 5p6. That's where it would be on the periodic table. We shift down here to the 6s level. We ask ourselves, well, is bismuth right there? The answer is no. So we have to write down 6s2. Is bismuth in the 4f level? No. So we need all those electrons, so 4f14. Is bismuth in the 5d level? No. So we need all those electrons, so 5d10. And then is bismuth in the 6p level? Well, yes. It's the third box, or 6p3 box, so we put down exactly 6p3. And again, that just represents the electrons, how we can identify those going forward. All right, so keep those charts handy. We'll use those, but that's how you write the electron configuration and the shorthand of the electron configuration. Let's keep moving on through our notes here. So what we need to talk about is orbital box diagrams. So in the orbital box diagrams, there are some rules that we must identify and know before we can write these orbital box diagrams. All right, so let's go ahead, let's just jump into these rules. And these rules, I don't need you to know the names, I need you to apply these. So the Apu principle says, hey, electrons occupy the lowest energy orbital. All right, makes sense. You go from low number to high number, okay? So remember with this that electrons will always occupy the lowest possible level And that just means we're going to go in increasing order, numerical order. Now, moving on here to the Pauli exclusion principle. And it says here that electrons must have opposite spins in the same box. So what that means is that each box can only have an up arrow and a down arrow. And this arrow represents an electron, okay? So the arrow is represented by an electron. So each of these things here, the up and down arrow represent the electron, and the up represents the one spin, and the down represents another spin of an electron. Then Hund's rule. Hund's rule says, hey, we can only add doubles or add pairs to boxes, orbital box diagrams or orbital boxes, if all electrons in a sublevel are filled first. Okay? Now, the other thing that I want to talk about here is each individual box is representing one orbital. And so with our orbitals, remember, it can only have a max of 2 electrons. Okay? So each box is representing an orbital, and we have to follow those rules. Now, it's easiest to follow those rules when we actually go through an example or a couple sets of examples. All right, so our steps. What we're going to do, we're going to write out the noble gas hand electron configuration. 2, we are going to draw the orbital box diagrams. And 3, we are going to place arrows following those rules as well. So let's go forward here. Let's go forward here, and let's do this business. So the first thing we want to draw is the orbital box diagram for silicon. Silicon has the symbol Si. So what I'm going to do here is represent silicon's symbol Si, and Si is element number 14. Element number 14, remember noble gas electron configuration, what we do is we go up one row to the right, we find Ne. Ne is what we put in parentheses, or excuse me, brackets, and then we start writing the electron configuration from Ne. Now, on our electron configuration chart, the Ne is right here at 2p6, so we go down to the 3s level. We ask ourselves, is silicon in that 3s level? No, we need all of those electrons, so 3s2. And then we ask ourselves, okay, is silicon in one of these boxes here? Well, the answer is yeah, it's this second box here in the 3p level, so we represent 3p2. Now what we do is this. We draw our orbital box diagrams. And I want to have a little side note out here, and that is this. That each sublevel has a distinct number of boxes. So an S sublevel is going to have one box. One box. A P sublevel, which I'm going to give myself a little bit more room here, is going to have 3 boxes or 3 orbitals. Okay? So 3 boxes or 3 orbitals. And then your D sublevel is going to have 5 boxes or 5 orbitals. All right, so again, 5 boxes here. 5 boxes, I drew 1 too many. Don't do that. 5 boxes should be represented by your D sublevel. Now, our final sublevel that we deal with is the F sublevel, which has 7 boxes that represent 7 orbitals. Now, I want you to notice a couple of things here, that these boxes are all interconnected, okay? So these boxes are all interconnected, and they represent each of those sublevels, which we've talked a little bit in section 2 about. Now, let's go through this. The next step says, hey, draw those boxes that correlate to each level. So we start out here with the S. The S has 1 box, so we draw 1 box. We also want to represent that we have the 3S level. So we put the 3S. Then we move to the P. The P has 3 boxes, so we're going to draw 3 boxes. Back to back to back. And we're going to put 3P. Okay? Now, this number right here represents the number of electrons that we have to fill these boxes. And we need to take it one sublevel at a time. So this 3S box is going to have a total of 2 electrons. Now, the first electron that we put is going to be represented by an up arrow. Okay? We ask ourselves, okay, is there any more boxes that needed arrows? No, there's only 1 box in this S sublevel. So to add in that second electron, we put a down arrow. Remember, the down arrow is accounting for that spin. Now we go to the 3P level. We block out our 3S and we ask, okay, how many electrons do we have to deal with? Okay, 2. So we always start out with an up arrow in the furthest left box. Now, what our rule that we just went over called Hund's rule says each box must get an electron before we go back and add doubles. They also must have the same spin. So we only have 1 more electron. We've already used 1 of those 2 electrons. The second thing that we do is we draw that up arrow, okay? So again, first one, getting used to this, we'll move on to fluorine. Fluorine, again, we identify its element F. So element F, and element F, we look and we identify for the first noble gas. Well, if you go up 1 and to the right, that should have been the box for helium. So we can go ahead and we can put HE in brackets for helium, and we turn to this. So helium, remember, would be the 1s2. So we go down to 2s2. Have we reached fluorine? No. So we have 2s2. We go over to the 2p level. Have we reached fluorine? Oh yeah, we have. It is the 2p5. So we write down 2p5. Then we write our boxes. We start out here with an S. S has 1 box, so we represent that with 1 box, and we write down 2S. Now, P has 3 boxes, so we put 3 boxes back to back to back, and underneath that, we write down 2P. Now we have to put our electrons in. So again, always take this 1 section at a time or 1 sublevel at a time. And we have 2s2. So we have 2 electrons. We always put our first electron as our up arrow. And then our second electron, if all boxes are occupied, which it has, we put it as a down arrow. Now the 2p box. The 2p box, we have to look at how many electrons we have to work with. Well, the 2p box, we have 5 electrons to work with. So, again, we have 5 electrons to put in these boxes. We always start here with an up arrow, and then Hund's rule says we have to put arrows in each box before we go back and add doubles. We have 5 to work with. So, I'm going to put an up arrow. They got to have the same spin in box 2. Box 3 is also going to get an up arrow. So right now we've used 3 of 5 of our electrons. So we put a down arrow to represent our 4th electron. So once we occupy the box with all up arrows, so each box has an up arrow, we can go back and add doubles. We've used 4 of 5. We go back to this middle box and add a down arrow. And now we've used the 5th of 5 electrons. So that's how we would write our orbital box diagrams. Okay? Now, we get to calcium, our last example here, and we show here calcium is box number 20. If we go up a row all the way to the right, the noble gas is argon, and so we start out here, calcium has argon as its first noble gas, and we turn to our electron configuration periodic table. So argon here would be at 3p6. We go down, we ask ourselves, is calcium one of these two elements in 4s? It is. So to write that, we just write down 4s2. Okay, now what we do is this. We ask ourselves, how many boxes does a 4s level get? Well, it gets 1. And then what we do here is we say, hey, that is a 4s level. And we ask ourselves, how many electrons do we have to deal with? Well, 2. So we put an up arrow for 1, and then we have another electron, so we put that as a down arrow. So all these are representing are where the electrons are, and it's specifying those orbitals. Now, the orbitals, which we represent by a box in this diagram, can be associated with those shapes we talked about in section 2. All right, so one last thing that we have to go over in this section of notes is our valence electrons. So our valence electrons are electrons in the outermost energy level. And the big thing here is they determine chemical properties. Now, we could take the time here and go over electron configuration and count the valence electrons, or I can show you a little shortcut. Okay, so again, let's talk about the steps, and then I'll show you this shortcut here. So again, valence electrons are going to represent the number of electrons in the outermost energy level, okay? So we get to this. We get to Lewis dot structures, or sometimes you'll call them electron dot structures. Well, it's going to represent dots that represent the valence electrons for each element. Major things here, we put the element symbol. Each side, we call 4 sides of the element symbol as 1. Each side gets 1 electron before you go back and you add doubles. So let's get to examples here. You can read over the steps here, but let's show you some examples. So our examples here are draw the electron dot structures for the following atoms. We start out with magnesium. The first thing that you do is you find the symbol. Symbol for magnesium is Mg. So you write down Mg. Now, you may be thinking, do I have to figure out, or I have to go through all of the valence electrons or all of the electron configuration to find out valence electrons? The answer to that is no. I'm going to show you a shortcut here. Our VE, or VE to the minus here, is going to represent, our valence electrons. So our valence electrons. So for group 1 has 1 valence electron. Group 2 has 2 valence electrons. We skip over this middle section and we go to the group starting with boron. Boron has 3 valence electrons. Carbon has 4 valence electrons. Nitrogen's group, all the way down here through bismuth has 5 valence electrons. Oxygen's group has 6 valence electrons. Fluorine's group has 8 valence electrons. And helium's group, I'm sorry, I made a mistake. Fluorine, this right here, has 7 valence electrons. I apologize for that mistake. Got ahead of myself. Again, big key thing here, 7 valence electrons for fluorine down in this group, 8 valence. So 7 and then 8. 7 and then 8. All right. Again, all we need to do is look here. We need to find magnesium. We go up and we say, hey, it's in that group that has 2 valence electrons. So we need to represent those 2 valence electrons with 2 dots. Okay? So we represent that with dot 1 and dot 2. Now, the dots have to go on different sides. It does not matter if you start here, you put a dot over here. You start at the bottom, put a dot at the top. As long as it has 2 dots and they're on different sides, that's good. So we go through and we find the next one, S for sulfur. Okay, so we start out with the symbol, S for sulfur. We want to know how many dots to put around sulfur. So we find sulfur, we go up. Well, we need 6 dots, all right? So 6 dots, we always start with 1 dot. We go around, and we want each of the 4 sides to have a dot. So right here, we have 4 electrons out of our 6 used. Now, once each side has dots, you can go back and you can add doubles. The other thing is that it does not matter what side gets doubles. As long as each side has 1, then you can put doubles anywhere you'd like. But again, no more than 2 electrons on each side. Okay? We go to bromine. Bromine has a symbol of Br. Symbol of Br. We go all the way up. And again, I made that mistake initially, but bromine's group has 7 valence electrons. That means we need 7 dots. So we'll start here by putting a dot around each side. That represents 4 dots or 4 valence electrons. Now we can go back and start adding doubles. All right, so again, use your periodic table. Use your periodic table here and utilize that to be able to find the number of valence electrons. Those represents the dots you put around the particular element symbol. Each side of the 4 must get a dot before you go back and you add doubles. All right, I know this has been a very long episode, but we packed a lot of information in here. And as always, I hope you have enjoyed this particular episode. And if you haven't done so already, make sure you subscribe.